Okay, now we have almost all what we need to build real programs. There's just a couple of little things we need more, and we're going to see them in this segment. So the first thing we need is the ability for functions to call other functions. This was already somehow implicit. If we define a function, we've extended the language, so implicitly you can also call a function inside of another function. But this is a particular ability, so we have to still make sure that the language has it. So this ability is called function composition. And with function composition, we can build a system in layers, where one function calls another one, that function calls even another one, and so on, all the way down. And unlike the universe, which is supposed to be turtles all the way down and never stops, this one, it eventually stops because we reach the hardware level of the system, the actual instruction set of the processor, and then the things stop. And if you look at the operating system, the middleware, the libraries, applications, there can be many, many, many layers. So dozens, hundreds, even thousands of layers. I don't know if anybody's actually counted them. It would be a very interesting and difficult task to count how many layers actually are being called. So this particular ability then to build a system in layers is what makes big computing systems possible. It means that a team of people can build things. You can call functions written by other people, and so on. So we can build much more than what we could do ourselves. So later on in the course, we'll really exploit this ability and extend it and consolidate it, and we will call this data abstraction. For example, one form of data abstraction is object-oriented programming. But let's not get ahead of ourselves. Right now, we're still in the functional paradigm, and let's see what we can do with function composition. For example, in the last segment, we saw the function sumDigits, which lets us build sum the digits of 3-digit numbers. Now, with function composition, we can build another function, sumDigits6, which lets us sum the digits of 6-digit numbers. So sumDigits6 will call sumDigits twice, once for the top 3 digits and once for the bottom 3 digits. So for example, function sumDigits6. So first we call sumDigits for the high digits, that's ndiv 1000, and then we call sumDigits for the low digits, and that's nmod 1000. So here we can define this. So I feed this to the system, and now we can call sumDigits6, and here, for example, on a number 314159, and this gives us 23, which is the sum of these 6 digits. Okay, so that works very well. We're using one level of function composition. But let's now see whether we can take the whole thing a step farther. The limitation of sumDigits6 is that it only works on a fixed number of digits, and sumDigits also had this limitation. So wouldn't it be nice if we could write one function that would work for any number of digits? How could we do that? Well, we can do that if we introduce a new powerful idea, the idea of a function calling itself. This is called recursion. So a recursive function is a function that calls itself. And that function call will call itself again and again. Seems kind of circular. When is it going to stop? But in fact, there's a simple way to make it stop. When the function calls itself, you just have to make sure that the argument is simpler. Simpler in the sense that it takes less computation to get the result. And if we continue in this, eventually we have an argument that takes no computation and the whole thing stops. So that way recursion can work. Okay, let's now define the function sumDigitsR, which calculates the sum of the digits of an integer of any number of digits, up to the limit of representation in the system. So how do we do this? Well, what we have to do is somehow do part of the work and then make a recursive call with a simpler argument. So how can we do that? Well, if we take ndiv10, we've removed one digit. So if we have the number 6561, we do div 10, we have 656. We've removed one digit. So that's simpler, less work. There's one less digit. So if then we take n mod 10, we pick off the lower digit, and then we can add that into the result, and then we get the answer. So this gives n mod 10, which is the lower digit, plus some digits r of n div 10. Right? So this is a simple definition where we take n mod 10, which is the lower digit, which is part of the result, plus, and then this is the recursive call where we have one less digit. Now this particular call is not going to work. And the reason is that nothing is stopping the recursion. Somehow we have to stop it. And the way to stop it is that when n gets so small that getting the result requires no work, then we have to break the recursion. And in order to do that, I introduce an instruction called a compositional, or an if statement. If n is equal to 0, then clearly the sum of the digits is 0. So the result is 0. Otherwise, if n is not equal to 0, then we can do the recursive call. So this gives us if n is equal to 0, then 0, else we do the recursive call. In this case, the recursion will stop. So here we can test it. Some digits are 314159, and as before, it will give us 23. Okay? Now notice we've used a new instruction here, the if. This is a conditional, and the if takes an expression here, n equals 0. It evaluates this expression, and this expression is what's called the Boolean expression. It has to return true or false, and the if then has two instructions following it. Here in the function body, these are these two expressions here, 0 and the bigger expression. And depending on whether the n equals 0 is true, if it's true, it takes the expression after the then. If it's false, it takes the expression after the else. And as all compound instructions in Oz, it ends with the end keyword. So notice we have introduced this new instruction, then the if, and we've introduced this comparison operator, n equals 0. Notice that we cannot use n equal 0, one equal sign, because it's already used as a binding for variable binding. So we need another symbol. So we have chosen to use the symbol n equals 0. Okay, so now we have come to a point where we have a complete, powerful language. So we have the ability to define functions, we have the ability to do function composition and recursion, and we have the conditional instruction, the if. With all these things together, our language has all the power that a programming language can have. We say that it is Turing complete. What that means is that it can compute the same functions as a particular theoretical machine called a Turing machine. And the Turing machine, as far as we know, is the most powerful computer we can build, has the richest class of functions that we know. That means our language is now just as powerful. It doesn't mean the programs are always going to be simple. Sometimes programs might be very long, but in principle, we can compute any function that be computed by a Turing machine.